All right, welcome to the review on motion of a line. We'll make this short and sweet. Motion on a line has to do with position, velocity, and acceleration functions. Hopefully remember that velocity is the derivative of position, acceleration is the derivative of velocity, or the second derivative of your position function. Speed is, of course, the absolute value of velocity. That's because velocity has a direction, right? Negative velocity means you're moving backwards. Positive velocity means you're moving forward. So speed would just be the absolute value of that number. Quick example question. This is asking for the maximum velocity attained on the interval from 0 to 3 by a particle whose position is given by this function. Well, if that's a position and is asking about velocity, I'm going to have to take the derivative, which I think I hid there. Yep. The derivative of that position would be this. However, it's asking for the maximum of that velocity. To find maximums, we take the derivative. So let's take the derivative of that so we can start finding maximums. Derivative of that should be 6t minus 12. Of course, the whole point of taking the derivative to find a maximum is so that we could set it equal to 0 and find those critical points. So 6t minus 12, set that equal to 0. All right, so I wanted to set the derivative equal to 0 so I can find my critical points. 6t minus 12 is equal to 0 means that 6t would equal 12, or just be a little faster than that, t is equal to 2. Now, one thing to be careful of, that's a critical point that's going to show me a maximum or a minimum if it exists on the internal thing there. I should definitely check if it is a maximum or a minimum, right? So I'm going to make my little sign chart. Spinning wheel, I'm going to have to edit out. There we go. So a little sign chart, put 2 right here. Check some value less than 2, plug it into my velocity. That'll get a negative velocity. Check some value greater than 2, plug it to my velocity function. Yeah, that's going to be a positive. So my velocity is changing from a negative to a positive, which means I don't have a maximum velocity at time t equals 2. I've got a minimum velocity. In fact, there's no maximum velocity on the internal interval at all. So that means if I do have a maximum velocity, it happened at one of the endpoints, right? Because my function is going to be going down, have some minimum at times t equal to 2, and then going back up. So like the maximum either happens here at this endpoint or there at that endpoint. At time t equals 2, we're at a minimum. So take those endpoints and plug them in. I'm looking for maximum velocity. So when I take this endpoint of time equals 0, I plug that into my velocity function. That's pretty easy to do in our head. If we plug 0 into that, I'll have a velocity of 9, right? 0 minus 0 plus 9. V of 0 for 0 seconds is equal to 9. If you plug the 3 in there, V of 3, that'd be 27 minus 36 plus 9. That's 0. So at 0 seconds, I've got a velocity of 9. At 3 seconds, I've got a velocity of 0. That's my maximum right there. Other velocity functions are position functions. All right, here we go. A particle is moving on the x-axis. This graph gives the position on the x-axis. So always make sure you know if the graph's a position function or velocity or acceleration, because it makes a difference how you look at it. If this is a position function and is asking when the particle is moving to the left, well, this gives its position. It was positioned at 1. Now it's something less than 1, right? Here is at position 2, and now it's going something less than 2. Whenever it's got a particles moving to the left, the derivative would be negative, or the slope would be negative. So that would happen whenever, let's see if I can type here, yep. Whenever, that would happen over the interval 0 to 1, and union 4 to 6. All right, going down there, going down there. When is it moving to the right? Well, it's moving to the right when your slope is increasing, right? When your velocity is positive. So that'd be from 1 to 3, and that's it. 1 to 3 seconds. What's a particle's greatest speed? All right, well, speed is the derivative, or velocity is a derivative of position, and speed is just the absolute value. So since derivatives give me slope, I'm looking for the steepest slope, which looks like it's going to be that's the steepest slope. Notice it said what is a particle's greatest speed, not when does it reach its greatest speed. So I'm not going to say the interval, I'm going to actually say the speed. So I got to figure out what the slope of this line is. Let's see here, that looks like the 0.4 comma 2. We're making some assumptions here. The AP exam will never have you assume these values. It'll actually tell you that's a 0.4 comma 2. But I forgot to label that before, so we're just going to say that's a 0.4 comma 2. And then this clearly looks like that's a 0.5 comma 0. So if you found this slope, that's a slope of down 4 over 1. Oh, sorry, down 2 over 1. 2 minus 0 is 2. So down 2 over 1. That's a slope of negative 2. But if it's got a velocity of negative 2, that means it's got a speed of 2. Right? Speed is absolute value of velocity. It's not just 2, though. It's got some units. So if I look over here at the units that the graph provided, x is measured in inches, time is measured in seconds. So the speed would be the absolute value of my velocity. It's just 2, and it's measured in inches per second. All right. Next one is again asking about moving left, moving right, and greatest speed, but this time they gave me the velocity function. So this here is a measure of velocity, not a measure of position. So same questions, but it's different. It says, when is a particle moving to the left? Well, so the left would be a negative velocity. Since this is measuring velocity, negative velocity would be during this entire part here from 1 to 4 seconds. When is a particle moving to the right? Well, that's when you've got a positive velocity. Oh, yeah, positive velocity. Positive velocity, since this is measuring velocity, it's positive over here. It's also positive over there. So a positive velocity would be from 0 to 1 seconds, and also from 1 to 6 seconds. Or sorry, 4 to 6 seconds. I think I said 1. All right. What is a particle's greatest speed? Again, this is giving me velocity. So I've got a velocity of -1 here, velocity of 1 there. Greatest velocity looks like it's way up here at a velocity of about 2 inches per second. That happened at the 6-second mark. All right. When is a particle speeding up? A lot of times AP exams will ask about speeding up or slowing down. Just make sure that if it's speeding up, that happens when velocity and acceleration have the same sign. If you think about speeding up, that means you're moving in, say, the forward direction and accelerating in the forward direction. That would be speeding up. Or maybe you're moving in the negative direction and accelerating in that same negative direction. That would be that would be speeding up, because you're already moving in the negative direction. And if you accelerate in that same direction, you're going to speed up. So speeding up happens whenever your velocity and acceleration match, when they're both positive or when they're both negative, because that way they're facing the same direction. You're speeding up in that direction you're already moving. When is a particle slowing down? That's when the acceleration and velocity have opposite sides, right? If you have a positive velocity but a negative acceleration, that means you're trying to go forward, but the acceleration is slowing you down backwards. If you have a negative velocity, it means you're already moving backwards, but a positive acceleration means you're accelerating in the forward direction. That'll slow you down. Sorry about that. There's a technical glitch, so I had to rewrite a couple things, but I'm back. This is a quick example about speeding up and slowing down. You're speeding up when your first and second derivatives are both positive or where they're both negative. If I take a quick pen here, I can see with this problem, I've got a positive second derivative over here because I'm concave up. And then I've got a negative second derivative here because I'm concave down. The information will always tell you where important things are. So here it says there's an inflection point at 1.5 seconds. So I know exactly right there, that's at 1.5 seconds. Right, maybe I'll even write that down there. I've got a horizontal tangent at 0.75 seconds. So right here, I've got a horizontal tangent. Maybe I'll put that down there, 0.75 seconds. And at 2.5 seconds, I've got another horizontal tangent right there. All right. So this problem was asking me, when is a particle speeding up? Well, here I'm concave up. And during that green concave up section, I've only got a positive slope from 2.5 onward. So the first and second derivative match signs, they're both positive from 2.5 seconds on over to the end, which looks like 4 seconds. But that's not the only time it's speeding up. It's also speeding up when the velocity and concavity are both negative. Here I've got a negative concavity. A negative velocity would be a negative slope. That happens during this section right here from 0.75 to 1.5. So when I'm speeding up actually over 2 intervals, from 0.75 seconds to 1.5 seconds, and from 2.5 seconds to 4. Slowing down is going to be the exact opposite of that, right? Slowing down would be when the first and second derivative don't match. Second derivative is negative here because I'm concave down, but my slope is positive. So my first derivative is positive. Those don't match, so I will be slowing down from 0 seconds to 0.75 seconds. And then again, starting at 1.5 to 2.5, because there my concavity is up, right, that upward curve, but my slope, my first derivative is down, going negative. All right, let's wrap this thing up. Last types of things with motion on line, we'll talk about displacement or total distance traveled. I've got a quick picture here. We'll kind of remember it. Displacement is another fancy word for net change, right? So if this is velocity, I know the integral of velocity will tell me net change, or integrals always give net change. So that'd be integral of velocity would be my net change in position. Here I move 4 units forward. It looks like meters, 4 meters forward, 2 meters backward, and then 2 meters forward again. Displacement is just the net change. Net change is going to be 4 meters forward. Because this 2 meters backward and that 2 meters forward, that's going to counteract each other, right? It's essentially balanced out. So the net change is 4 meters forward. When it asks for the total distance I traveled, however, that's going to be, right, I'm counting moving backward and moving forward. That's total distance. It'd be 4 plus 4, 2 plus 2. That'd be 8 meters total distance. So definitely pay attention when they ask you about movement, if it's talking about a displacement or a net change, or if it's talking about total distance. Last question says, find the final position of the particle if S of 0 equals 7. That means I'm starting at the 7 meter mark. Well, if I started at the 7 meter mark, and then I move 4 meters forward, 2 backwards, and 2 forwards again, that means I've just got a net change of 4 from that 7. So the final position would be 7 plus that net change of 4. I'll end up at the 11 meter mark. That's all there's to it. For those of you who like having something to kind of write down, here's just in general. If anything ever asks about net change or net change in position, sometimes they'll use the word displacement. That's just the integral from A to B of your velocity function. If, however, it asks for total distance traveled, then we have to treat our negative velocities as if they were positive. And so that would be the integral from A to B of the absolute value of your velocity function, because that'll take all of your negative velocities and count them as positive. If you're doing it by hand, I would just split it up and like find this for the integral of that would be -2, but you would just call it a 2. The integral of that is 2. And so you just say, hey, instead of calling this as a negative, we're going to count that as a positive. And then final position is just your initial position plus your displacement. Don't forget your initial position. They'll often give you an initial value of some sort. When it asks for a final, like how many ducks are there at the 5 o'clock? Then you're going to have to take your number of ducks you started with and then add the number of ducks that changed. So don't forget that part. Really quick question, if like that, if you want to, sure, let's do this one quick. So as a particle moves along the x-axis at a rate of r of t equals this thing in inches per second. If the particle is 7 inches to the right of the origin at t equals 3 seconds, where is it at 10 seconds? What's the total distance of the particle traveled during that time? I read that really fast. It can be hard to follow. But just look what it's asking. It gave you a rate. It's saying the particle started at the 7-inch mark. And then it's asking where is it at the 10-inch mark. So that's saying, hey, I started at 3. I started at the 7-inch mark. I'm adding some kind of net change, and particularly I want to add the net change from t equals 3 seconds to t equals 10 seconds. That's just going to be 7 plus that integral. I'll share that screen with you because I've got that already written down on a graph. Here it is. So here's the equation. That's my r of t. In fact, I'm going to call this r of t instead of f of t. There we go. There's my r of t. This is my rate of my velocity. So this is how my x particle is moving along the axis. And I believe we said it started at 7-inch mark, right? And then I'm just adding the net change from 3 seconds to 10 seconds. So I go to my calculator. I want to find the integral from 3 seconds to 10 seconds. And that 7-inch mark, that was at time t equals 3. Let's find that integral. I'm just going to write r of t because I can. I already named it up here, r of t. So r of t dt. Looks like I'm going to end up at the 22-inch mark. The second part of that question did ask the total distance traveled over that time. Again, be careful here. This is traveling backward. I could go to the work of trying to find this 0. It's not hard. There it is, 4.7 and 6.58. And I could find this area and that area and this area separately. Or, to make my life easier, I could just find the value of that integral again. This is a velocity, right? But in this case, since I want to find the total distance traveled, I want the absolute value of that velocity. So total distance traveled of 18 inches. I'm not worried that that's smaller than 22, because remember that's saying where it ended up its position. The net change was 15 plus the 7 from my initial starting part. So I ended at the 22-inch mark. That 18 inches, that's the total distance I traveled from 3 seconds to 10 seconds. All right, that's it. There's an assignment on Schoology. It's a 2018 free response. Free response tends to be a really good one for emotion online problems, so give that one a try. If you want some extra practice, there's some optional extra practice here in the 97 and 98 exam. See you later.